So we're going to do the basics of capacitors. As I'm sure you guys know, the very standard capacitor is going to be two parallel metal plates. So I'm going to try and draw them slightly 3D just for fun. And one of them is going to be charged, or both of them are going to be charged, my mistake. And then, good enough. So if you put a positive charge down this plate and an equal negative charge down this plate, what does the electric field look like inside? Well, in the middle sections, it should be straight line from positive to negative. Straight over. But on the outside, like, I don't have as much of an effect of these other guys pushing it in. Because, like, here, let's say here, if I'm at this point, let's kind of move this side. If I'm at this point, it's in the middle, so this charge is going to have an effect and have some forces going in this direction. But this charge is going to have the opposite effect and it's going to cancel out. So towards the edge, you actually don't get some of that canceling out. So you actually get some of your field lines to start to curve away. And then they'll curve back towards the other plate because they're still attracted to the negative. So you're going to get a little bit of bowing here. And farther out, you can even get a little bit more. So here's something that looks like that. And so the field inside should be constant. So the electric field inside, we're usually going to use the formula that the potential is equal to the electric field times the distance between the plates. So I'm not going to bother to define E and V for you, but I'll write D. So in this drawing, I'm going to go from same edge to same edge, because it's 3D. Your D would be there. Yeah. So now another way of thinking about this, of course, would be we could have written this formula the other way, and we could have said E equals V over D, depending on what you're given. If you're given potential or if you're given electric field. So how much charge can we store on a capacitor? Because each capacitor is a little bit different. So our definition of capacitance is going to be C is capacitance is Q over V. So most of the time you're going to see that written as Q equals CV. But really this is how we're defining capacitance, kind of like how Ohm's law is more of a definition of resistance. And that's why you get some funny behaviors when your temperature changes and things. Your resistance isn't always linear with it because it's not based on that. It's based off of just the ratio of voltage over current, right? So, I mean, similar thing. So people often use it like this, but this is I think more of the fundamental form. So what are the units of capacitance? Well, I mean, we could write it like, could be coulombs per volt, and a volt, I'm sorry, volt, I wrote joule. I was getting a little bit ahead of myself. And a volt is a joule per coulomb, right? So we could write it as coulombs over joules over coulombs. So that would let us do coulomb squared per joule. But and then we could write all these out in terms of fundamentals if you really want to. I could write coulombs as amperes seconds because coulombs aren't fundamental, even though that would make more sense. It's defined in terms of the ampere. And then a joule is a kilogram meter squared per second squared. So we're going to cancel quite a few things out. Actually, no, this would be additive, right? Yeah. So, but in the end, like, all this is complicated. We have a special unit for it. So the unit that we are going to use is F, the farad, named after Michael Faraday. So another important equation that we care, a couple more important equations, but the next one we care a decent amount about is going to be the question of how much energy is stored in a capacitor. So we're going to use U for potential energy. It's going to be 1/2 capacitance times the voltage or the potential difference across it squared. And then just to fill out our equations, our next equation is going to be the equation for capacitance based on shape. So and as you remember, a capacitance is a measure of how many coulombs of charge you can put on each plate per volt you apply. So it's going to be C equals epsilon A over D. I think some people write it slightly differently in different order, but that's all the same. I should point out though that I've written epsilon here instead of epsilon naught. If the capacitor doesn't have anything between the plates, we'll use epsilon naught, but in the case it has a dielectric, we'll use epsilon. And I'll talk more about dielectrics later, but just know that for dielectrics, epsilon is equal to some constant, kappa, times epsilon naught. Alright, I'm going to call it quits here, guys, and I'll see you in the next one.